That's the JPL solar system ambassador.
Very good, very good.
For the great state of Tennessee.
There you are, from the middle of the country, where you guys get horrific ice storms.
Yeah.
But John has agreed to come here with the work and the help of Marine and STEM to talk to you guys. You guys are first on the list, and then I'll visit with my astronomy class at 10 o'clock. And we're recording it so that we have a good record, and John's been most gracious to let us do that. This is important information. You guys know as well as anyone that we're trying to move vigorously into the area of investigating the sky and the radio as well as the visible spectrum. So without further ado, I'll get out of your way because I'm kind of short on time.
Thank you, Mark. Appreciate that. Thank everybody for having me here. It's a real pleasure and delight to visit your campus. And I respond to hey you, but no. Actually, if you have a question throughout, you can go ahead and interact. Okay, I'm going to talk a little fast. I hope you don't mind. All right. So the first thing I want to do is just refresh your memory about the electromagnetic spectrum, since after all we are interested in light. This is how we observe the universe in all kinds of light, optical, radio, whatever. And it's an interesting cartoon here because it shows you the extensive range. So it's almost like a logarithmic curve, if you wish. We have miles or feet to miles and wavelength here to sub-angstroms on the other end. So it's a tremendous dynamic range. And to remind you about light too being electromagnetic in nature, what's really cool about light is that depending on what part of the electromagnetic spectrum you're in, how we detect it, the terminology changes. Like for example, for really high energy stuff, we look for energy being deposited to detectors, and they're called detectors. On the other extreme end, where you have a very low energy, like radio or microwave, we call those detectors, instead of calling them detectors, we call them antennas. And it's because it really responds to either the electrical or the magnetic component of the electromagnetic wave. And then what we can see is kind of like in the middle. And so we call them a number of things, eyeballs, telescopes, etc. Okay, so the light that's coming from the universe, from outside our planet, only some of it can get through. Visible clearly can get through. A lot of the radio can get through, but the universe is pretty. The atmosphere is pretty opaque to many of the wavelengths, and sometimes all the stuff in the UV or whatever. And we're thankful that we do have this kind, not only because we need oxygen to breathe, but the ability to screen out a lot of the ultraviolet. But not all of it. I mean, you still need ozone and things like this, otherwise we're in big trouble. But anyway, it's a complex response, as you can see, where exactly the windows are. The optical and radio have a nice, optical and some microwave, infrared rather, gets through, and the radio's got a big old hole there, which is great. So we can look at the universe right here from the Earth because of the transparency of our atmosphere. Well, exactly what gets through when it comes to radio, the ionosphere, because of the influx of radiation from the sun, whatever, it ionizes the atmosphere above our breathable atmosphere to produce an ionic layer. And this layer has a bunch of electrons and ions in it, and they're just moving around. And depending on how many you have and how they're moving around will determine what external wave can get through. And it turns out that if the wave isn't able to wiggle fast enough, okay, it won't be able to get through. It just bounces off like a mirror. And that cutoff is around 20 megahertz, depending on the season, 15 or 10 megahertz. So usually 20 we use, though you might get some coming through. That's megahertz. So that puts us right in the high frequency range of radio. And we'll see that this is really important. Well, we'll see in the next lecture. This is really important because there's a kit or a radio telescope that you can build with dipole antennas, that's tuned to 20 megahertz, and at 20 megahertz, it's fairly noise-free, and we can listen to the sun, to Jupiter, to even the galaxy rotating through the field of view of the antenna. Okay. So how do we produce radio waves? We produce radio waves in three major ways of doing it. Something called continuous thermal sources, continuous non-thermal sources, and discrete sources. And what we mean by that is thermal sources is basically a result of the motion of ions to each other. For example, well, I've got a cartoon here showing it. I'll backtrack on the slide. That's basically what I want to show you. As these ions are in motion, right? So as an electron, say, sees the field of a proton, it's deflected. Its course is deflected. And as you know, whenever you have from Newton's law, where a body will remain in motion or still unless acted upon by an external force, okay? And if there is such an external force, then that body will experience an acceleration according to Newton's second law. So we see that an electron zipping past, because it's lighter, it moves faster, almost 2,000 times lighter than the proton. It zips by, sees a proton, and may be flung or deflected, okay? So that electron is going to be changing direction. Even if the speed is the same, the fact that it's changing direction, a change in velocity, either magnitude or direction, will produce an acceleration, right? So we have an accelerated charge. And the thing about accelerated charges is that they emit radiation. They emit energy in one form or another. And some of this energy is emitted as radio. So that's what I mean by these continuous thermal sources. They're called free transitions, and we see them in places like when the sun is quiet, the Orion Nebula. I thought I saw a picture of the Orion right there. Certainly like it. It's not the Orion.
I think it is. I think it's a different one.
Okay, it's a different one, but I'm sure that one too as well. Because why? Because we have hot stars in the middle of these stellar nurseries, hot OB stars, which means that they're emitting a lot of ultraviolet radiation, ionizing the stuff around them. Okay, so you have a lot of these electron ion environment where the things are zipping around and it's emitting these radio waves that we can pick up, and that's kind of cool because we want to be able to pick up some of these things as an amateur, at least, radio astronomer. So I'm not going to get into that, except I just already said it. Okay, now, do I really want to talk about this now? Yeah, I guess so. This whole concept of having a swarm of electrons and just matter, just like our sun, picture a big old ball of plasma up there. That this you'll hear the expression that we can treat a lot of these hot bodies like black bodies, and the black body is not a trivial concept, and I'm not going to spend a lot of time on it, but suffice it to say this, that you can think of matter as a bunch of little springs, and you know when springs they can flex and oscillate if you give them an inkling to like a little heat. Okay, they'll go more heat, we'll do more of this. Well, you know, some springs are stiff and some are soft, and so just imagine a system which has a bunch of springs with different stiffnesses, so that they vibrate at different energies, really. Okay, because remember, the elastic energy can be like proportional to the square of the displacement. Okay, square for a normal mechanical spring. So you can think about these things as little reservoirs of elastic energy. All right. Well, just like when you push a swing, another kind of oscillation system, when you push it, if you push it in sync with the way that it's already moving, then you can make it go bigger. You can make it. It'll take my effort. It'll take my energy, so to speak, and respond. If you don't, then it'll duck and it'll stall or do some other weird things. All right. So these things are called resonances. So what's going on with matter in general is you have all these little springs. Light comes. Remember, light can deliver energy. Light comes, and if the light delivers the right energy, it can excite these little springs. But they're all different. So there's going to be a range of energies. All right. So not only can something absorb these energies, but they can, by reciprocity, emit it as well. And so normally we speak of matter that's at a certain temperature will exhibit a certain response to the light. Okay, so here we see a picture of something called the spectral radiance. It's kind of like a power thing. The light intensity, it's kind of a light intensity thing against the wavelength, and we see that it goes to a peak and then goes off and comes back down again. Well, what we often hear is this. We hear that this thing here, this is what we normally see. We see over here, this thing is called the spectral radiance. And the units are energy. This is kind of a weird unit. Joules per square meter doesn't make much sense. Joules per cubic meter would. That would be like an energy density. But an energy surface density is a little weird. So if you do a trick, you multiply top and bottom by reciprocal seconds, or hertz, then what do you have? You have joule hertz, which is the same thing as joules per second, or a watt per square meter per hertz. Ah, now that makes sense. Power density per unit bandwidth, all right? Well, what I'm not saying also, what a lot of these pictures, when you go to the internet and you look at them on various books, they'll leave out something very important. This is tacitly assumes per unit angle. We call it a stereoradian. Okay, because if you look at the surface of if you look at a sphere, okay, the surface area is 4 pi r squared. So it kind of like subtends an angle of 4 pi. So what we see is sometimes we see this thing. This thing is oftentimes called B. Sometimes people call it I. But the important thing to realize is what I have up there is B lambda. Okay. Notice B sub lambda, and I have it B sub lambda because I have it in terms of the wavelength. Let's see, what is it? H squared over lambda to the fifth, right? Let me show you something. This right here, hc over lambda kt minus 1, all right? This right here is a result of the distribution. This comes as a result of Bose and Einstein, the distribution of, and remember all the springs I was just telling you about that can have a whole wide range? Well, this kind of tells you like how they're distributed, how that energy is distributed. And that's what makes this thing actually peak. Without that, you would have something like this. And that's of course not good, because Mother Nature, as we know, as we realize, as we study her, does not like discontinuities. She doesn't like infinities. And when I say she, it's just a term of perfection. Okay. So the thing is this, that if you take this curve, notice that each one of these curves is for a specific temperature. All right. This is what's normally taught in astronomy classes, is that, well, if you take this curve and you see where it peaks, where the maximum, where the peak light is at, we call it lambda max. All right. There's a relationship that the reciprocal absolute temperature is proportional to lambda max. We usually see a number there about the proportionality. I deliberately left it out for this reason. We say, oh, let's look at our sun. Our sun is, we see it's yellow. Oh, okay, where's this curve for our sun? And what you'll see in almost every textbook is that our sun is about 5,800 degrees Kelvin, and lambda max puts it right in the yellow peak, so to speak. Okay, so we say our sun is yellow because of that. The answer is wrong. Our sun is white. Look, when I look up there, I see yellow. Yeah, there's something called scattering. The same reason that we have red sunsets and red and orange and yellow sunsets is because when the sun is low to the horizon, a lot of that light gets scattered. The blue light gets scattered away. The higher frequency light gets scattered away, leaving the reds. A similar reason exists for why our sun appears to be yellow. It's not because of that. When you actually look at this curve, when you actually look at this, you can tell exactly where it is in the visible spectrum. It's really hard to tell. So we meaning astronomers, do not use this thing called the Wien displacement law. We do not use this to determine the temperature of a body. You might do that on the test. All right, well, if it has a peak wavelength of 5,400 angstrom, what's the temperature? Well, then you can calculate that. At best, it'll put you in the ballpark. Why? Because suppose you looked at this guy. Wait a minute, I'm not drawing it right. I'm not sure if I can draw it right. Suppose you constructed that radius curve, that spectral radius in terms of frequency instead of wavelength. Well, you say, well, wavelength and frequency are related to each other pretty easily, like that, right? Meters per second, reciprocal seconds. Okay, so I'll give you meter. This is the relationship between wavelength and frequency. But if you were to take this guy and substitute it in there, you're not going to get the same result. You're going to get something different. Radius sometimes waning. I'm going to cheat. Look, too much keep square. I don't want to spend too much time on this. Same factor over here. But the point that I want you to concentrate on is this thing here does not translate into that. Okay? Well, that means that when you were to get the maximum peak over here, this new, for the maximum here, it's not going to give you the same result as this. If you use this curve, you're going to get something in the yellow. If you use this curve, you're going to get something in the infrared. This they don't teach you. Most books do not even mention this. We don't use this. The reason I bring it up is that we don't use this. Radio astronomers, especially, don't use these Wien formulas. What we do is we observe the object at various frequencies and then curve fit it to the equation to get the peak temperature. That's the way we actually do it. All right. So what's going on here? What's really cool is you can derive these things pretty easily because you all had calculus. All you have to do is take the derivative of any one of these. Say, okay, and set it equal to 0, and then when you do it, you'll derive where the maximum is. So that's a fun exercise. You should do it. It's easy to do. It's not hard. It may look hard to differentiate this, but trust me, it isn't. This is really easy to differentiate. Okay. Well, what about the other piece of calculus that we like? That is to say, the area under the curve. All right. What about the area under the curve? All right. This is. Let's just take the frequency one for example. All right. The area under the curve is going to be summing up all the pieces. Okay. We'll give you the area under the curve. Well, what are the units? The units are watts per square meter per hertz times hertz. So watts per square meter. Okay. So watts per square meter, which is the power density, or equivalently the energy flux, is what you have. Again, we're assuming we know about this, so we really have to take this into consideration. So actually then, if you take the area under the curve of this one, Since it's the same source, it should equal the area under the curve for this guy, right? And I'm going to put in there the solid angle just to be completely correct. All right, and we're integrating overall the frequencies, overall the wavelengths. Okay, I'm getting sloppy here, I'm sorry. All right. The area under the curve is going to be the same. And what are we going to find when you do this interval? You're going to find that you need some help because you probably haven't had enough math how to solve that interval. What interval are we talking about? Real quick, just because you guys are physics, that's why I'm doing this. You'll end up with an interval that looks like this. It looks fairly innocent. It's called, some people give it a name, I don't give it a name. You can't solve this integral using your standard integral techniques. You have to use something that's called complex integration. And when I mean complex, I'm not talking about complicated, I'm talking about complexes in real and imaginary. You're dealing with what's called a contour interval. I'm not going to go into that, I promise you. Contour interval.
But John, the main point is you're trying to find the total energy output of a particular star.
And when you solve this problem, you'll end up when you get this integration here, it's going to give you a constant and the absolute, the fourth power of the temperature. This is called the Stefan-Boltzmann law, which is really cool. And if you do that, I'll just tell you right now, you're going to end up with the Riemann zeta function with an argument of 4, which is pi to the 4th over 60, I believe, if I remember correctly. And this is the gamma function, which is 3 factorial. No. Hold on, something's wrong. I'm out. I don't remember. This whole thing comes out to be like pi to the 4th over 15 or something like that. Okay, this is the factorial function, this is the Riemann zeta function. So these guys, you have to look at the table is what I'm getting at. All right, I've spent enough time on that stuff, I want to move on. I just want to show that this is really some really neat opportunities to do some physics and math. And that's how a lot of times we learn new math techniques, because we're running across a physics problem. How do we solve this sucker? So you have to kind of like step aside and go, how do you solve something like that? You know, you can't. Right now, you guys would be stuck looking at a table somewhere, which is fine. All right, let me move on. Continuous non-thermal. Okay, what do I mean by non-thermal? Non-thermal meaning not caused by just this free transition, but rather the magnetic forces themselves can deflect the electrons. For example, you have a charge flying past the magnetic field. The magnetic field will cause that charge to go around it. Okay, so you get this deflection, and again, as long as you get this deflection, you're going to get some radiation emitted. And now, depending on the strength of the magnetic field and the speed of that electron, most of the electrons, will determine what kind of radio waves come out and the quality. All right. The really cool thing is that these things, unlike the other radiation I showed you, which I didn't really talk about, like you can think of the electron as a little dipole antenna. The radiation pattern, instead of coming, okay, hold on. Picture time. I did draw a picture. The electron that's going in the circle, okay, like this, will have a radiation pattern that looks like that. Okay, it's perpendicular to the orbit. But as this guy speeds up, what's going to happen is, and here I'll try to, here's my two lobes, my arm and my two lobes. As I speed up, as I go faster and faster, then these two lobes are going to do this. And so, if I go fast enough, those lobes will be very point it in the direction of my motion, okay? This is what's called, it's hard to draw, but these two lobes is in the direction of motion. This is perpendicular, now this is parallel to the plane because everything's zoomed in down. This is what we call synchrotron radiation, synchrotron. The synchrotron means relativistic, basically relativistic, well, looking like close to the speed of light particles, right? Well, what if they travel much slower, but they do the same thing? Then we call it cyclotron. Cyclotron is non-relativistic. Synchrotron is relativistic, okay? And we almost never see any cyclotron stuff in most astronomical sources. The energies are such that we see always synchrotron. All right, that's the purpose of all these. And I just and where do they come from? They come from like when stars rip themselves apart. You get these shock waves. You get violent explosions. These things that accelerate the electrons tremendously. And the magnetic field out there in interstellar space may not seem very big. They may be microgauss, micro Tesla even. But combined with the speeds, there's enough deflection for it to produce a synchrotron radiation. Yeah.
John, do we have those? We don't have those in our atmosphere. These types of radiation.
No, not in our atmosphere. No, our atmosphere won't be producing any of these. No, these are not high enough. No, not in our atmosphere. Our ions are just moving. If anything, we would probably look like a thermal source. If you could just look outside and sense our atmosphere, we would look like a thermal source. Okay. Some examples. So I mentioned the sun when it's quiet, but when you have sunspots, these are regions of a lot of magnetic disturbance. Okay, so you'll see synchrotron radiation from them. You'll see them from the like the aurora borealis and things like that on other planets and various other objects. Okay, and then finally, discrete sources means that all over the place, but rather selective. And the most important one comes from what we call the hyperfine transition. Steric transition that happens when you have hydrogen, which the universe is ubiquitous with. This is the most abundant element because it's the simplest one. You have the proton and the electron together, all right? This is unionized hydrogen. They can spin individually. They do spin individually. When they're spinning in the same direction, that's a slightly higher energy than when they're spinning in opposite directions, which is called spin paired, in a lower energy state. The difference in that energy happens to be, if you were to actually look at those two energy states, calculate that energy difference, it happens to be right in the radio range of 1.4 gigahertz or 21 centimeters. And this is the thing that we love because there's a lot of that out there, a lot of hydrogen. So we can look, we can find, we can see the radio images of various images, meaning the signals. We can make images from them, not easily, but we can. So this is the most important transition. There are other ones. Hydrogen. Remember what hydrogen? I can show you a picture. Just I'll point it out to you when I get to it. Here it is. Here's the picture I want to show you. See this? This is an energy level diagram for hydrogen. And if you notice the blue lines, they're like rungs of the ladder. They start to get closer and closer together. They telescope. Okay. There's only a few lines shown, but way up there, when n gets to be over 100 or several hundred, that the energy spacings between, say, the line 200 and line 201 would be in the radio. You see, so you can get radio emissions from highly excited hydrogen atoms. Okay. Now we can't meaning amateurs, can get those things. We need pretty sensitive equipment to be able to see those, all right? But in principle, that's where they are, okay? And I just like the colors. That's why I think I stuck this one in here. "Oh, be a fine girl, kiss me" is the mnemonic is sometimes used for the star classifications. It's and that, as you notice, that the hot stars, the O, B stars that I mentioned earlier, are in the tens of thousands of degrees as a black body, compared to our sun, which is down here G, a G star about 5,000 degrees. And then we get much cooler stars, like the cooler on the outside. Don't be mistaken. On the inside, it's an inferno. But they're down in the 3,000 or lower degree range. Okay. So, in radio, we want to look at mostly millimeter to decameter range, typically, and so that's what we normally that radio range we look at. Now, sub-millimeter, you'll hear the expression sub-millimeter, but when you go to sub-millimeter, what do you mean sub-millimeter? Remember, this is wavelength. All right, a millimeter is like 1,000 microns, right? And light, visible light, is a half a micron, to give you an idea. So as you go from visible light, what's right beyond red, we call it infrared, all right? That's like around 800, no. That's like around a couple of microns, okay? And then beyond that, you're gonna run into, well, there's the whole range of them. You're gonna bump into microwaves, okay? Which would be in the order of a centimeter or more. 30 centimeters. It's a ballpark number. So as you go longer and longer, okay. So sub-millimeter means that we're in that range that it isn't really radio. It's really microwave or infrared. But radio astronomers like to call it sub-millimeter radio astronomy. Okay. In order to do sub-millimeter radio astronomy, you need a huge, flat dish, like the Green Bank telescope. I mean, you have to have a flat, meaning a perfectly smooth, flat, I meant a smooth surface. The surface irregularity has to be less than about 1/6 of what you're trying to measure. You can imagine trying to get something as smooth as that, something that gigantic. That's a real challenge. That's why it's outside the range of anything examiner. Plus the electronics at those high frequencies becomes extremely expensive. You can't deal with this stuff that you build here. You have to start putting things in liquid helium and all kinds of things like that because of their sensitivities. All right. So, what I didn't mention to you earlier was this thing here. When I put the units down here, joules? No. Watts? Where did it go?
I
may have erased it. Okay, well, that watts per square meter per hertz is we give that, we honor one of the radio stuff inventors called Jansky. We just call it a Jansky. Notice the unit, 10 to the minus 26 watts per square meter per hertz. It's an extremely small amount of energy. You can put all the energy that's been emitted for all time, so to speak, in a teaspoon. It's just a tremendously small number. To give you a sense of appreciation that what we're trying to detect are really weak signals. And when you're trying to detect weak signals in the midst of noise, all kinds of special engineering challenges happen. And that's part of the fun, is to overcome those challenges. So for us, a strong source would be for anybody, a few Janskys we would be able to detect, but we would not be able to detect something that's a millijansky range. Forget that. All right, we need something that's several tens of Janskys, maybe even 100. I'll have a table with relative strength for some of these soon. But there was two guys basically. I just mentioned Jansky. There's this funny looking telescope antenna This is at a Green Bank, National Radio Astronomy Observatory in Green Bank, West Virginia. And it's still there, this antenna, or a replica of it, I guess it is now. And this Jansky was basically working for the communication company, Ship-to-Shore Communications, and he was tasked to determine the source of interference. And so he found that the source of interference, because it seemed to appear there was an extraterrestrial interference. And so basically the problem was solved in the sense that their communication problems, issues ship-to-shore was solved, but they didn't let, meaning I think it was Bell Labs he was working for, I'm not sure what it was. I forgot. But the thing is that he had to move on. But fortunately, this guy from Illinois by the name of Reber carried on with his own homemade dish. He carried on the studies, and he found, he was actually able to get a rough idea of our galaxy by looking at those emissions. And so that was really, in the early to late 30s is when radio astronomy was born. And radio astronomy probably really took off as really a result of World War II because of the development of the transistor and the radar electronics, some pretty sophisticated circuitry and such. So radio astronomy has been really a boon. Why? Because more than 75% of what we know about the universe comes from radio astronomy. Why? Because when you look out there at night, like you did last night, you might see a bunch of pretty stars, but you're really limited to what you can see. You can't see in the middle of our galaxy, for example, because all the gas and dust is there. Radio waves can penetrate that. So we can get an idea of what's inside, and in galaxies as well. All right. So your basic radio telescope is you have some kind of, say in this case, what's showing is synchrotron radiation, but it could be any kind of radiation, any kind of radio wave coming down. The dish, basically, the light comes. Why a parabola? Because a parabola has this property of having a common focal point, unlike a spherical section, which does not have a common focal point. Okay, so well.